Hello, students. This is the fourth in a series of videos on the topic of nuclear chemistry. Videos we have looked at nuclear notation, used that notation to do nuclear decay reactions, and described half-life in simple terms. In today's presentation, which is the fourth part, the Road to Fission, we will look at a more sophisticated way of describing and predicting half-lives, which is more realistic. We will then turn away from the normal and natural decay processes that we've described previously to talk about processes that are actually don't occur that much naturally on Earth, fission and fusion. And then in particular, we're going to look at a chain of historical events that ultimately led to the development of the first atomic bomb and the beginning of the nuclear age. So let's get to it. Previously, when we looked at half-lives, we had problems that made a very powerful simplifying assumption. We assumed that we were always working with a whole number of half-lives. And while that does simplify the math and allow us to introduce the concept, it's not very realistic. After all, nature is very unlikely to give us a sample that's precisely one or precisely two half-lives. To deal with those situations, we're going to need a better kind of math which is able to model exponential decay. Here we see several different exponential decay curves. They all have the same general shape, but every isotope will actually have a different curve. The different curves will have similar shapes because it's a similar process, and there's math that will describe that process, but we have to be able to have math that will deal with a curve rather than a straight line. When we have a curve, that means that the shape of the change or the rate of the change is constantly changing. The math has to be able to handle that. To handle that, we're going to introduce some new buttons on your calculator. And one button will use this number, which is called Euler's number. This is a number that is a mathematical constant. It is roughly equal to 2.718. It is an irrational number. That means that you can't represent this number as the ratio of two whole numbers. And like pi, it is a transcendent number, which means it can go on and on and on. Its decimal expression is indefinite, perhaps endless. How do we get this particular number? By repeating the following operation. 1 plus 1 divided by n, and that entire expression taken to the n power. The n is simply the number of times we choose to do this operation, which is multiplication. And it's multiplication essentially raising this number, this operation, to an exponent. And you see one way to represent this is that we have a big weird looking e, that means the sum. It's the summation of all the possible operations of 1 over n factorial. And practically what this means, it means 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3. And you can get the idea. It will keep going on and on. And the more we do this operation, the closer we're going to get to 2.718. Now, a button that uses Euler's number is found on your calculator. And this is a function that is called e to the x, which in turn is related to another function, which on the calculator will appear as ln. Sometimes we say natural log. This is the base of natural logarithms. And these two functions usually share a button. With this calculator, you see that there's a big button that says ln, and then above that, as a second function, there's e to the x. Now, the reason why they share a button is because they are related functions, and they can be thought of as two different ways of describing the same phenomenon. So if we're going to use these two, if there are two different ways of describing the same phenomenon, we should see some similarities in how these functions operate. Now, the natural logarithm of some number x, which we often write ln x, is simply the power that Euler's number must be raised in order to equal x. Now that's kind of awkward when we say it in a sentence, but if we consider some examples, it'll make it easier to understand. Here we have e to the 0, and e to the 0 is said to be equal to 1, which is no surprise because any number raised to the 0 power is 1. And e to the 1, well, it's approximately 2.718. While the natural log of 1 is 0, and the natural log of 2.718 is 1. So there's a symmetry there. E to the 0 is 1, natural log of 1 is 0. E to the 1 is 2.718, natural log of 2.718 is 1. Now this, again, might seem confusing to you if you haven't had a third-year math class, but again, you can think of e to the x and natural log as being related, but different ways to describe the same exponential process. Now here are the actual 4 equations we're going to use. And these equations, just like e to the x and natural log, these equations are going to mirror one another because they describe similar phenomena that are related. So we have one equation that says n sub t equals n sub 0 e to the negative kt power. And we have another equation that says natural log of a sub t equals natural log of a sub 0 plus negative kt. And again, we're going to use these to figure out things. For the equation, the second equation, the one that uses natural log, this is mostly useful when we're talking about the percentage that's likely to remain. We'll often do a percentage with these. And the other equation is even more useful. N sub t equals n sub 0 e to the negative kt. This is a very powerful equation that's used in all kinds of activity, human activity, not just in science, but in business and in commerce, because this is a function that can be used to model not only exponential growth, but it can be used to model a car loan, a house loan, or the rate of return on an investment in the stock market. And you know, these are really fundamental mathematical operations in our economy. So it's a very powerful equation. Now, which one of these is better? I don't know. I happen to find the first one easier to solve, and the first one also is useful for solving problems with where you're trying to find the number of grams or the number of atoms or perhaps the number of moles. So it may be a little bit more flexible, a little bit more adaptive than the second equation, but they are mirror images of one another. And to show that, here we go. Notice that both equations have a term that's sub T. That means the amount of that substance, of that isotope that is still present at a certain time, labeled T. Each equation has a term that has sub-zero. This is the amount of that isotope that you started with at time 0. And each equation will use this relationship, negative kT, where K is the decay constant for that particular isotope, and T is the amount of time that it is decaying in this particular case. Many times we will not be given K, but we will be given the half-life, and so we will have to calculate K from the half-life. And to help you do that, we have this set of relationships, which also is like a mirror. So again, these two are the equations we'll use to solve for amounts after a certain amount of time. And they are related and they mirror one another, as you see. And then half-life itself and decay constant also mirror one another. So notice here we have one equation that says T1/2. That's the half-life. The half-life equals the natural log of 2 divided by the decay constant. The natural log of 2 is approximately 0.693. So there we see it. Half-life equals 0.693 over K. But we also have another equation which is used to find K. And in this case, K equals the natural log of 2 divided by the half-life, which means K equals 0.693 divided by T1/2. And you can see the symmetries here. You know, we have half-life and the decay constant. We can see how they match up. And of course, both equations use natural log of 2. Both equations use 0.693. Now, for these half-lives that occur naturally and the various other decay processes, alpha and beta decay, gamma and positron emission, electron capture and alpha bombardment, all these types of decay that we've talked about before in our notes of nuclear reactions, these are reactions that kind of occur on Earth all the time due to natural causes. They don't usually require a lot of energy, and the amount of energy that's required is something that can occur on Earth. But we're now going to turn our attention to reactions that under normal conditions almost never occur on Earth. And fusion. On the item on the left is fission. You can see it's a relatively large nucleus. We're hitting it with a small target that's like or a small projectile that's like a bullet. And it breaks the large nucleus into many smaller daughter products, and it releases a certain amount of energy. Next to it on the right, we have fusion. Here we have several very small chunks of matter being pushed together to make a slightly larger chunk, and this is fusion. So we have two similar words, fission and fusion, but they are very different processes. Fission breaks something, fusion pounds. Now, these kinds of nuclear reactions don't normally occur on Earth because usually there's not enough energy on Earth, but these energetic conditions in which they can occur are common in the universe inside stars. Stars are simply gigantic balls of gas, much more massive than a planet like the Earth. And because they are much more massive, they have incredible gravity. And the center of a star like our sun applies a gravitational force that is many million times greater what is found on the surface of our Earth. And the energy of this gravity is so great that atoms of hydrogen and helium inside our sun are constantly being pounded together. And it often happens that we get these high energy reactions, fusion reactions. And in the fusion reaction, atoms of helium will come together and they'll form a heavier element, and part of the mass before and after the reaction is converted into energy, which gradually escapes the huge gravity of the star. And that is why the stars shine. The reason why stars shine is that you're seeing energy being released from nuclear reactions inside their core. In fact, a star is nothing more or less than a gigantic natural nuclear reactor. Now, while these reactions are unlikely to occur on Earth because the energy is not likely to be available, we've learned how to artificially provide the necessary conditions for those reactions to occur. And it takes getting a certain kind of matter in a very small space and applying a lot of energy to it. But when you do these reactions, you can get even more energy out. It takes a lot of energy to trigger them. They don't naturally happen on their own on Earth, but if you can figure out a way to trigger them, they can release even more energy. The energy that's stored inside the nucleus is many orders of magnitude more powerful than the energy that's stored on the outer edge of the atom in the bonds between the electrons. And so being able to liberate this tremendous amount of energy has changed the world. We're now going to tell a story, a series of historical events about the Road to Fission, about the series of events and things that had to happen in order to get to the point where scientists could start to figure out how to liberate that huge amount of energy. It begins in 1895, where a German physicist was looking in a darkened laboratory, and he was looking at a device that you see in front of you. It's a glowing tube called a Crookes tube. It's coated on the inside with a molecule that, when it's hit with charged particles, will glow. And he was testing one of these because this had become a popular device, because over in England at Cambridge University, the British physicist J.J. Thomson had used this device to deduce the existence of the electron. So this German physicist was trying to study that, but he was trying to study in a dark room, and he was looking for certain phenomena, and he didn't want any light to interfere. So he had one of these tubes, but he covered it completely with black cardboard so that no light could actually escape from the tube. And inside his dark laboratory, he turned on the device. No light came out of the black cardboard covered tube, but over at his desk, there was a sample of a substance that had recently been provided for him just sitting on his desk, and quite unexpectedly, that substance in the dark laboratory began to glow. The scientist was puzzled. He turned off the power to his glowing green tube inside the black cardboard, and as soon as he did, the substance on his desk quit glowing. He turned the power back on, it started glowing again. Wow, quite by accident. Scientist Wilhelm Röntgen realized pretty quickly that what was happening was that there was radiation that was invisible to his eyes that was passing right through the black cardboard and coming out into the room and causing certain substances to glow. And he gave this radiation the name X-rays because just like now, the symbol X is often used to mean an unknown variable. And see, he didn't know what it was, so he called it an X-ray. And he realized that they were so energetic they would pass right through most substances. Now here on this slide, you see a picture. This is the first X-ray picture. It was taken a few days after he discovered it. The story goes is that his wife came to the lab and he switched on the device, and while it was pointed to the screen that would glow, it had the same kind of molecules on it that the inside of Crookes tube did, and they saw a shadow cast on the screen by the invisible rays coming out of the tube. But it wasn't a shadow of his wife's hand, it was the shadow of the bones in her hand and the ring she had on one finger, because the X-rays actually pass through the flesh. You have to have something more solid to stop it. Well, scientists quickly learned that this invisible radiation was being released by all sorts of naturally occurring heavy elements in the environment, like uranium. Shortly after this, a Polish chemist who studied these substances noticed that the rocks that contained these extra heavy elements that were releasing radioactive particles, she noticed that if you left them on a balance and took their mass and came back a certain time later, that their mass had gone down. And she reasoned that what was happening is that as the atoms were actually falling apart and losing mass, and somehow that was causing the sample to release energetic particles, and she's the one who gave this phenomenon the name radioactivity. Super important work. You see her here in the illustration. She and her husband and another scientist are working, studying radium. This is a radioactive element that is so radioactive that it actually glows in the dark on its own. It radiates light. So Marie Curie discovered this radioactive element, and she named it radium. And she was Polish, and her husband was French. And so she named another element she discovered, also radioactive, polonium. And she named a third element, also radioactive, francium. And, she's discovered several elements. And her work was so important that she's one of the few people to ever win 2 Nobel Prizes. Very important. So Marie Curie was an experimental scientist, just like Röntgen. But here we have a case of a theoretical scientist that you've heard of. This is Albert Einstein, of course, very famous, most famous scientist of the 20th century. At the time this was going on in 1905, he was not really working as a scientist. He was working for the Swiss government, doing patent applications. People would send him descriptions of ideas, new ideas, or new inventions, and he had been hired by the government to investigate certain kinds of new inventions to see if they were actually new enough that they could get a patent from the government. So probably not that interesting work. In his spare time, though, when he wasn't shuffling papers for the Swiss government, Albert Einstein was doing science, sort of. He wasn't doing experiments. What he was doing is he was using new ideas, trying to come up with math to explain the new ideas, and then writing papers based upon the new ideas and the new math in which he attempted to explain things that hadn't been explained before. It's theoretical. He didn't actually do experiments. But in the year 1905, he wrote not one, but 4 separate papers. In one of these papers, he proposed the speed of light was a constant. Wow. He proposed that all descriptions of motion were relative to the point of view of an observer, which is an idea that we now call relativity. And most importantly for this presentation, he claimed that matter and energy were related, that they were equivalent. And this is when he proposes a set of math that leads to the most famous equation that anyone's ever heard of. Everyone seems to have heard of this equation, even if they don't know what it means, E equals mc squared. And what Einstein was claiming when he talked about mass-energy equivalence, he said that the rest energy, the energy of an atom at rest, E, equals the mass of that atom times the square of the speed of light. Pretty deep stuff. Now, Einstein's ideas immediately suggested an explanation for the radioactivity that Marie Curie had described. She saw that the mass of the sample was going down as it was radiating, energy. And so Einstein says, look, what's happening here is that some of the mass is actually being converted or being translated, you might say, expressed as energy. Now, once people discovered that you could have something that would shoot out invisible radiation, it was natural for scientists to try to use the invisible radiation as a tool to figure out other things. So here we have Ernest Rutherford, who was a student of J.J. Thomson at Cambridge, who had discovered the electron. And this is a famous experiment that has been mentioned before in this course. He had a sample of a radioactive substance. And that radioactive substance was put inside a lead block. And there's a little pinhole in the lead block, and it shoots a beam of particles at a target. And what Rutherford was actually trying to do is he was trying to use these little particles, what he called an alpha ray, what we would now call an alpha particle. He was trying to use this kind of radiation as miniature bullets. And his target was a piece of gold foil, gold that had been pounded very flat until you had something that was only 1 or 2 atoms thick. And he would shoot these little particles at it. And behind the setup where the gold foil was, he had a screen. And the screen was coated with the same kind of molecule that's inside a Crookes glass tube or on the screen that Röntgen used to take the first X-ray photograph. It's a molecule that, if you hit it with an energetic particle, it will glow. And so Rutherford's idea was, I'm going to shoot these miniature bullets at the gold foil. It's going to bounce off and it's going to hit the screen behind, and wherever it hits, it'll glow. When the charged particle hits it, it'll glow for a while, and you'll be able to measure where it hit. So that's his idea. And that's what he's trying to do. But just like Röntgen discovered X-rays by accident, Rutherford got a result that he wasn't expecting, which was the more important thing. Every now and then, one of these particles, instead of hitting the screen, would bounce straight back. And that could only be explained if it had hit an atom in such a way that it had hit dead center. And in dead center, there had to be something very dense, very massive, and very positively charged. And that's how Rutherford explained it. Rutherford had discovered the atomic nucleus filled with positively charged protons. Well, this was a very famous discovery. And just like Thomson had won a Nobel Prize for discovering the electron, and just like Röntgen had won a Nobel Prize for accidentally finding X-rays, Rutherford won a Nobel Prize for accidentally discovering the protons in the atomic nucleus. Pretty important discovery. And eventually he was put in charge of the same Cambridge laboratory that J.J. Thomson operated when he was a student. And for the next several years, Rutherford and his students continued to use alpha particles to split atoms and do experiments. One of Rutherford's students, a guy named James Chadwick, used a variationist technique to discover the neutron. And by 1932, Rutherford had been at this for nearly 30 years, and he could write an article about this new discovery of the neutron. And in that article, he could tell you everything else that he and the other Cambridge researchers knew about the atom. And so he wrote this article, and anyone who was interested in this topic read it because it pretty much told you everything that was known. And in this article, Rutherford, while talking about the newly discovered neutron, he speculated that neutrons would be the next bullet. Instead of using alpha particles, which are relatively large, the size of an entire nucleus of helium, Rutherford speculated that you would be able to use a neutron, which is about 4 times smaller than the nucleus of an alpha particle. You could use it as a smaller bullet, and in the future that you could shoot neutrons instead of that, the smaller bullet, and you would probably be able to discover things that you couldn't discover with alpha particles. Now, Rutherford himself was skeptical about the idea that you would ever be able to get energy out of the atom, but people knew there was energy in there, and they were interested in studying the atomic structure, and, it led to a lot of Nobel Prizes. Now we come across one of the truly remarkable figures in the history of science, a person who was super bright and had great intuition and had great drive, but he was not an experimental scientist, and he had a strange approach to trying to get the experimental scientists to listen to him, to work with him. He was a theoretical physicist from Hungary named Leo Szilard. At the time Leo Szilard had his great breakthrough, he was living in England. He had left his country of Hungary because things were getting difficult for people who were of Jewish ancestry. fascism was on the rise in Europe. And Szilard had a certain amount of money saved up, life savings, so he just left Hungary and went over to England, where Cambridge University was, and he started trying to learn English and get work in the scientific community. And he had a strange way of doing this. He would go up to somebody that he knew was a famous scientist, and he would introduce himself as if he was just as good as they were, even though he was a nobody. No one knew anything about him. And he would say something like, "Hello, my name is Leo Szilard. I've been studying this. I'm very educated. I'm very bright. I have very good ideas. You should give me an idea. You should give me a job. You should let me come work for you. You should do experiments to test my ideas." And if you think about it, if you're a total stranger coming up to someone who's a professional scientist and talking to them like, they owe you a living, they should automatically listen to what you have to say, you may realize intuitively that that may not be the best way to build relationships. So he was kind of a strange character. So he couldn't get regular work, and one evening he was walking out of a theater. He had just seen some movie, and it was raining. It's England. England's an island nation. It rains a lot there, and it was nighttime, and he looks up at the night sky as he's getting ready to cross the street, and the night sky is really well illuminated by the brilliant lights of the theater marquee. As he looks up in the sky, he can see the raindrops coming down, and he even sees some raindrops kind of going sideways, and some of them hit other raindrops, and raindrops combining to make new raindrops. And in that moment, he had a flash of intuition, because right before he'd gone to the movie, he'd read Rutherford's article, and he was thinking about it, and he realized that if you do nuclear reactions and neutrons come out of those reactions, those neutrons could hit other atoms. And if they hit other atoms, they might be able to break them, and then one could release even more neutrons, and then you'd have a chain reaction. Maybe all of the atoms would react, not just one. Well, Szilard realized that if you could find a way to trigger a reaction like that, you could release a tremendous amount of energy. And he knew that this was a powerful and valuable idea. And he also knew it was something that you would want to advertise to the people back in his home country who were persecuting people of Jewish ancestry. You wouldn't want to be telling fascist countries that were aggressive and building up big armies. You wouldn't want to necessarily let them know, hey, there might be a way to get tremendous amount of energy to make a bomb. So what Szilard did is very different. He filed for a patent. Einstein was working at the Swiss patent office. Here in the United States, we have the U.S. patent office. Well, he was in Britain, so he filed for a patent with the British patent office. A patent on, hey, we could use neutrons to break atoms, to do a chain reaction, to release all this energy. And the British government gave him a patent. And then he went around to scientists and said, hey, I'm Leo Szilard. I've come up with this idea to release nuclear energy. I've got a patent on the idea. You should do research and support me. Now, that's a little bit better than, hey, I'm a nobody, but give me a job. But he still had trouble getting people to take him seriously. Now, the same year that Szilard received his patent, Marie Curie's daughter, Irene, was all grown up, and she and her husband, Frederick Joliot, they announced that they had made artificial radioactive elements. They'd taken ordinary matter, and they did what Rutherford was doing. They bombarded that ordinary matter with alpha particles. And what happened was they produced new versions of that ordinary matter that was radioactive itself. Why was it radioactive? Because it had absorbed extra mass, and they'd become extra heavy isotopes and somewhat unstable. But they'd done this with relatively ordinarily low mass elements. And so they won the 1935 Nobel Prize in Chemistry. Now you should be noticing something. All these characters are winning Nobel Prizes, right? Röntgen, by accident, discovered X-rays. Nobel Prize. J.J. Thomson, Nobel Prize. His student, just by accident, Ernest Rutherford, discovers the nucleus. Nobel Prize. Rutherford's student, Chadwick, discovers a neutron, Nobel Prize. Einstein comes up with just some math ideas to explain what's going on, Nobel Prize. And now you have Marie Curie's daughter and her husband, they're winning a Nobel Prize. So you can see that this is an active area of research, and the people who go into this field get rewarded. Learned that the very next year, a group in Italy, led by a man named Enrico Fermi, they took Rutherford's suggestion seriously. Instead of using alpha particles as their bullet, they began using neutrons, just as Rutherford had suggested. And instead of using low mass elements like Irene Curie had done, they used the heaviest elements they could get, which included uranium, and they pounded that uranium with neutrons. And as a result, they got new products. And these new products had mass that was greater than any known element. Something new had appeared. So Fermi interpreted the results to mean that new elements had been produced, and he named these elements that were heavier than uranium, the heaviest naturally occurring element. He named them transuranics because they went beyond uranium. So that's what Fermi thought. I don't want you to think Fermi's a bad scientist, but he's an excellent experimental scientist. But he was not a theoretical scientist. And it turns out that his explanation of his own experiments is incomplete. Fermi won the 1938 Nobel Prize for his pioneering work. But this lady, a chemist named Ida Noddack, pointed out he had failed to account for all the products of lower mass that his experiment had also produced. Fermi had an explanation for the new heavier elements. I've made new elements by making things heavier. But what's the explanation for the lower mass particles? He also gets lower mass particles. And she was a brilliant woman. In fact, she probably set a record for most times nominated for a Nobel Prize and didn't win. It is conceivable that when heavy nuclei are bombarded with neutrons, these nuclei could break down into several fairly large fragments, which are certainly isotopes of known elements, but not neighbors of the irradiated elements. That is, they were known elements and they were probably radioactive, but they weren't right next door to the elements that were being hit with the bullets. They were elsewhere, distant elements elsewhere in the periodic table. So what Noddack was saying is that the lower mass products might have been the result of fission, splitting the atom. You might be getting these lower mass products because you were taking some atoms and you were breaking them through fission. And that was a better explanation for those lower mass products than fusion, which is combining atoms together to make heavier things. No doubt Fermi did succeed in doing some fusion reactions, but there were also fission reactions happening, and he did not come to that conclusion right away. Eventually, and you will see this, eventually Fermi was confronted with evidence that showed that his own interpretation of his Nobel Prize winning work was incorrect. Now things get serious. From inside Nazi Germany, a bombshell. Up to this point, this has all been very theoretical. Scientists are winning Nobel Prizes, but their motivation is to deduce the atomic structure, to try to figure out what's going on down there inside the atomic nucleus, to try to understand the relationship between different atoms and these processes that produce radiation. But this experiment takes things into an entirely different realm. This was an attempt by two German chemists, Otto Hahn and Fritz Strassmann, and they were trying to duplicate Fermi's work. They were doing the same thing. They were taking the heavy element uranium, they were shooting neutrons at it, and they were expecting to get similar results. But instead of getting transuranic elements of greater mass, at the end of their experiments, some of the mass was missing, and the main thing they found was a much lighter element, which was barium. And they were completely baffled because, again, they were experimental physicists, not theoretical ones. They weren't necessarily inclined to find a theoretical solution. Now, these fellows had a partner who was a theoretical physicist, but she had suddenly had to leave the country. This was a scientist from Austria who had been working with Hans and Strassmann in Germany, And she had been working with them for several years, basically living in the same town, meeting with them regularly. She was partners in all their research. She knew that they were excellent scientists, and she was very familiar with what it is they were trying to do, that they were trying to simulate results. Now, Meitner had to flee very quickly. In fact, Hahn and Strassman had given her a gold watch and, essentially several $1,000s of money, and then they'd smuggled her out of the country because people like Lee Meitner were being persecuted in Germany, just like people like Leo Szilard were being persecuted in Hungary. So the story goes is that she was living in Sweden at the time, and they sent her a letter to explain privately what's going on. And she was on a picnic. Apparently, it might have been a romantic date. And she didn't open the letter right away. She took it with her in their picnic basket as they traveled to some location where they were going to have a picnic. Now, at the time that this event happened, it was widely believed that you couldn't get two alpha particles to come out of the same nuclear reaction. But part of the results that Hahn and Strassman sent to Meitner said, well, we're getting a mass. We got a mass of over 100 nucleons. That's about the same mass as 25 alpha particles. And so what's happening here is you're getting a loss of mass that is 12 to 13 times greater than what you should be getting. It doesn't make sense, and they don't understand what's happening, and so they turn to the theoretical physicist, their colleague, Lee Meitner. Well, the story goes is Meitner took out the letter in the middle of her picnic, began to read it, and within a few minutes she pulled a paper napkin out of her picnic supplies and grabbed a pen, and on the back of a paper napkin wrote an equation. Meitner knew that her colleagues were excellent experimentalists and they would not be making a clumsy mistake. So even though the result they had went against what everyone else thought was true, she said, well, let's assume that they got it right and that everyone else is wrong. And Meitner steps outside of the normal path of science, and she takes a bold step. And she says, here's what I think happened. You're shooting neutrons at uranium just like Fermi did. So in the equation, you see 1 over n, that represents a neutron. You see 235 over 92u, that represents an isotope of uranium. And she says what happens is you probably got barium-141 as one of your products, which means that you have 95 unaccounted mass units. And she says, I think 3 of those unaccounted for mass units are separate neutrons coming out in the reaction. And where's the other 92 mass units? Well, she said you made a gas. You made the gas krypton. Specifically, you made an isotope of krypton, which is krypton 92. Why don't you see it? Why is the mass gone? Because while barium and uranium are both solids, krypton is a gas. And so it just instantly spreads out and you weren't aware of it. She said, here's the equation. This is what I think happened. You actually broke the atom. It's nuclear fission. Here's what you need to do. You need to repeat the experiment inside a vacuum chamber, so if any gases are produced, you can capture them and determine what gas it is and determine its mass. And Hahn and Strassman did exactly that. They created a trap for gases, and they detected krypton in the right amounts, and they published their findings in a German science journal. Now, Meitner did not win a Nobel Prize. Hahn and Strassman did, because they did the experimentalists and because they did the main publication work. But everyone understands that Meitner actually explained their finding. And she never won a Nobel Prize, but later on she did have an element named after her, Meitnerium. So there's that. This thing gets published in late 1938, and it goes into a journal, and scientists read journals about other people's work. And Leo Szilard was now living in New York. Specifically, he was living in the island of Manhattan. He had gotten tired of having the door slammed in his face trying to get work with the British scientific community, so he'd come to the U.S., and he was back to his old tricks. Hello, I'm Leo Szilard. You may not have heard of me, but I've been doing important work for 5 years. I have patents on nuclear energy, a cutting-edge idea. I'm a smart guy. You should give me a job. He was going around doing what he was doing, had done in Britain, trying to go up to total strangers who are professional scientists and get them to do work for him. Again, he's coming up to people who are experimental scientists who have worked for years to get in the position. They have big, expensive labs, and they're already doing experiments of their own. And basically, Szilard is coming up to them and saying, quit wasting your time with those experiments. Instead, you should be hiring me, and you should be testing my ideas. So, again, not the world's best way to influence people. So he's living in New York City on the island of Manhattan. He's got a little apartment, and it's hot. He takes a bath, and while taking a bath, he gets the German journal, Naturwissenschaft, and he reads Hahn and Strassman's article, which includes this description of this reaction. And he realized instantly that this equation, Meitner's interpretation, was the kind of equation that could sustain a chain reaction, just like the one he had imagined 5 years earlier, and that a reaction like this could be used to build a bomb. So what does he do? He goes and visits Fermi. Does he go to Italy to visit Enrico Fermi? Nope. Szilard goes and sees Fermi right in New York City, right in Manhattan. Fermi's living in Manhattan just by coincidence, just like Szilard. Why? Well, Fermi's wife is Jewish. And Fermi decides he needs to get out of Italy for the sake of his wife, just like Szilard left Hungary, just like Meitner fled to Sweden. There's a similar problem at work here. So Fermi is not a nobody. He's a somebody. He's won a Nobel Prize. And so when he decided to leave Italy and go to New York City, he had no problem getting an amazing job. He was hired right away as a professor and head of a research program at Columbia University, which is the Ivy League university that's on the island of Manhattan. He's doing work there. And so Szilard knows this. So he goes and visits Fermi. And it turns out Fermi has already read Lise Meitner's paper himself, and he realized that his own Nobel Prize winning work probably failed to detect fission. Szilard comes right up to him and says, "Hello, I'm Leo Szilard. You don't know me, but I'm a genius. I have 2 patents on nuclear energy, and you really should stop what you're doing and work with me." And Fermi didn't care for him very much. Leo was a theoretical physicist, and he was an experimental physicist, and Leo is basically reminding him that, oh, by the way, your interpretation of your own Nobel Prize was wrong, wrong, double wrong. But nevertheless, Fermi does understand that Szilard knows stuff and that he has been working on this a while, so he agrees to work with him. And they design the first nuclear reactor. It's a little test device. It's no bigger than a typewriter, no bigger than a laptop computer. And they test it. To test it, they have to have their own source of uranium. There's almost no uranium in the United States. And I can't make this up. What happens is Szilard takes his life savings, buys a car, drives across the U.S.-Canadian border illegally without a passport, buys 500 pounds of uranium, and drives back to New York. Szilard was a difficult person, but he was a very determined person. So they get the uranium, they purify it, they attempt to do the reaction, and inside this tiny little reactor, they get a result. The reaction happens. They measure the energy. Nuclear fission is a reality. So at this point, the possibility that the fascists in Europe, the people who have chased out people like Szilard and Meitner and Fermi's wife, it's a real alarming prospect that they might read the same paper and try to do atomic energy and maybe make a bomb. So Szilard, what does he do? He goes and alerts Einstein, who is also living in New York. Einstein's not living in Manhattan. He's on Long Island, but he's living in New York City. And because, Einstein also Jewish, also fled Europe to get away. So he visits Einstein. Einstein listens to Szilard, understands what he says. They both work together to write a letter. Szilard does most of the writing. And eventually, the final draft of the letter, Einstein puts his name on it, and they send it to President Roosevelt. The idea was that since Einstein was the most famous scientist in the world, a letter coming from him would have special weight. Roosevelt received the letter weeks before World War II began. Didn't make a decision on it right away, but very quickly after the war began, he authorized what was known as the Manhattan Project, and it got its name because both Fermi and Szilard were living in Manhattan inside New York City. And they started this project before the U.S. got into World War II, because Roosevelt had it explained to him that you don't want the fascists in Europe to get the bomb first. You just don't want that. You want to make sure the United States is the one that gets this first. Because if you have to go to war with Germany and they have this vastly superior weapon, you can't win. So in 1942, Fermi and Szilard scale up their research. They want to show that they can control the reaction. So to control the reaction, they got to scale it up. They've got to make it way bigger. And they do it in a secret Chicago lab. Now, I cannot make this up, ladies and gentlemen. They built this under the bleachers on the football field at the University of Chicago. It was a secret, and they built it underneath there. In this illustration, you see blocks of graphite. That's a version of carbon. They were solid carbon. They drilled holes in these blocks so they could anchor them like bricks. They surrounded them with a wooden superstructure, and they used rods of an element called cadmium. And they would insert the rods into the pile. When the rods were fully inserted, when they would try to do the nuclear reaction, the uranium would react, it would release neutrons, it would decay, but the cadmium rods would absorb the extra neutrons, and so no reaction got out of control. And what they did gradually is they would pull the rods out so that there was less and less of the cadmium in there to absorb neutrons and to increase the rate of reaction. Eventually, after several trials, they succeeded in showing that they could have a self-sustaining reaction which could be controlled with these rods to release energy. So the government, while this was going on, they essentially built secret cities from scratch. I'm not exaggerating. Hanford, Washington, Oak Ridge, Tennessee, and Los Alamos, New Mexico were three separate communities that really didn't exist prior to the Manhattan Project. The government poured personnel in there. They didn't tell them what they were actually working on. There were hundreds of thousands of people employed at these cities that were built from scratch in these locations. They had different functions. The main function of the Los Alamos site is that this is where a group of scientists were going to focus on the challenge of designing the actual bomb. Pictures of some of the scientists involved. For example, Fermi is in there, but his name is not shown on his badge. It's just his code name. He was G24. This may have been the greatest collection of brains ever working on a single project. There were about a dozen Nobel Prize winners on the project at the time the project began, and after the war was over, there were another couple dozen scientists who worked on this project who also ended up winning Nobel Prizes. So very smart people. Their problem was they had to figure out how to get the bomb to go off, because you needed to have the uranium fuel in a very tiny space, and you needed to pound it, all the atoms together so tightly that it would force them to break. But how could you do it? So they had to come up with a design to make it happen. Eventually, they came up with a design that used dynamite charges. They had a core of uranium surrounded by dynamite charges, all of which would push in on the center of that core and force the uranium atoms to come so close together that theoretically it would trigger it. The device was called the gadget, and they mounted it at a tower that they built at a site in New Mexico, which is now called Trinity Site. They hauled it up with a winch, and you can see that the gadget is surrounded by plywood and tape to conceal what it actually looks like. You can tell it's very hot there. One guy's in shorts, another guy's in t-shirt. They've got plastic screening up surrounding the top of the tower. Hey, you know what? It's the New Mexico desert in the middle of the summer. It's kind of hot. Here's what the gadget looked like when it was unpacked. You see there's a whole bunch of different wires coming out of it. That's because they have to have all the dynamite charges go off simultaneously at exactly the same time. And it's also because the gadget was rigged that when it went off, that it would trigger a whole bunch of electronic recording equipment, still and motion picture cameras, that had been developed just for this situation. They had to figure out how to make slow motion cameras, which really hadn't existed before. And they made a couple of cameras that could take 1,000,000 frames a second. They're not like, this is not like our cell phones, which are just computers and they're capturing light directly on a sensor. They actually had to have physical film, and they had to have a gadget that would rotate the physical film up to 1,000,000 times a second for 1,000,000 separate pictures. So that was an impressive technical development. Well, this is one of the first pictures that was taken. This is a still image, and it's taken 0.016 seconds after they detonated it early on the evening of July 16th, 1945. What you're seeing is actually not light. The sky is completely dark because it was dark time, and the film is not really all that sensitive to visible light. This is a film that's sensitive to X-rays, and so you're seeing an image of X-rays that was produced. And if you look at the very bottom at the horizon, you'll see little bumps, and those bumps represent yucca plants, which are giant cactuses 10 to 15 feet high. The tower would have been about 10 times taller than the yucca plants, and you don't see the tower because it's already been vaporized. The fireball doesn't actually appear in this picture. The fireball only comes another fraction of a second later. Initially, the only thing that comes out is gamma rays and X-rays. So that was the first of the atomic blasts, and of course, eventually it led to wartime footing. The Trinity bomb announced that for better or worse, the era of nuclear fission has arrived, and as a result, the world would be forever changed, and that is true. There are many good products of nuclear fission and ultimately nuclear fusion. There's many good products of this nuclear technology. It's not all bombs and dangerous stuff, but you need to know about it because it's very likely that in the future that you live in, that more and more electrical power will be generated through nuclear power, and you would want to have nuclear power to be safe and reliable and not weaponized.